So that was kind of just describing each of those forces separately. And what we'll do now is really sort of just putting all of that together. Because in actuality, our cells don't compartmentalize or distinguish these forces. Both these forces are acting on our cell membrane simultaneously, okay? So we're putting these forces together and thinking about the sum of both of these forces, both the chemical and the electrical forces, and then thinking about how our different particles will move depending on combining those forces. So in this illustration here, we've got a negatively charged environment inside the cell. We've got a positively charged environment outside the cell. And if we consider an ion like potassium, potassium is at a higher concentration inside the cell and a lower concentration outside the cell. And so if we think about our chemical driving force on potassium, it wants to move outside the cell, okay? It wants to go from high concentration to low concentration. But if we think about the electrical driving force acting on potassium, potassium is also a charged particle, so it also has to obey its electrical driving force. It's going to want to be getting back inside the cell. And so this is why we want to think about both these forces and combine them, because they could actually be moving the particles, or let me say wanting to move the particles in two opposite directions. And so we want to combine these forces and think about which force is, stronger, which of these has a stronger magnitude, and which one will outweigh the other, which force will overcome and move the particle in that general direction, okay? And we're also going to be speaking about what's called the equilibrium potential. And that is another potential that wants to bring potassium, for example, to its equilibrium, bring these concentrations to equilibrium so that there's equal concentrations on either side. And that is essentially what's driving this chemical movement. It wants to see equal amounts of potassium on either side. And so we think about the equilibrium potential, and it's the membrane potential value at which potassium is at equilibrium. And what this value means is that when the cell is negative 94 millivolts, potassium is at its equilibrium. In other words, potassium is no longer moving because both sides have equal concentrations of potassium, okay? And that'll make a little bit more sense as we go on and kind of add some layers to that, add some clarity. So if the chemical and electrical driving forces are acting in the same direction, we're simply going to honor that general direction, right? That's the easy, sort of the straightforward of the different options that we have. So we're combining electrical and chemical, and if electrical wants to move a particle into the cell, chemical wants to move that particle into the cell as well, then the overall force is going to be, obviously moving the particle into the cell. And in terms of the magnitude of that force, we simply combine the value of both of those forces individually. So it's just a sum total of chemical and electrical force, and then the direction is going to be favoring the direction, which is the same direction of both of these forces. Now, things get a little bit more complicated or more tricky if the chemical and electrical forces are acting in opposite directions, as we just described with potassium. It had a chemical force moving out of the cell to balance its concentration. It had an electrical force simultaneously acting to move it into the cell. And so we want to think about netting that force out and figuring out which of these two forces is stronger. Okay, the electrochemical force acts in the direction of the stronger force, and then the magnitude will simply be the differential. So I'm going to take my stronger force, which may be acting in one direction, subtract my weaker or smaller force, which is acting in the other direction, and I'm going to end up with a smaller value in the general direction of the stronger force. Okay, so the larger force minus the smaller force moving in the net direction of the stronger force. Okay. Now, let's look at a bit of a teaser question before we move on. So the question is, if a chemical gradient existed, right? So we have a differential in terms of the concentration of a particle on either side of our cell membrane. Under which condition would a particle not be transported across the membrane, even if the membrane were permeable to that particle? So let me kind of reword or rephrase that. So if we have a chemical gradient, right, but we still don't see movement, the particle for some reason doesn't want to move, what can we deduce based upon that if our membrane is permeable to that particle? What would explain why we're not seeing movement, although we have a chemical gradient? Given what we said above here, so I'll kind of give you a minute to play around with that in your mind, and then we'll talk. So given what we just described at the top here, if we had a chemical gradient which would want to move a particle from high to low concentration, what would have to happen for us to not be seeing that particle move? I'll give a little hint. So it has to do with the electrical force on that same particle. What would the electrical force need to look like for there to be no movement? Okay, I'm not seeing any response, and that's okay. I mean, we'll go on and explain this in a little bit, but I'll wait another few seconds. All right, so let's talk about this. So essentially, we have a chemical driving force. We have a concentration gradient. Let's say we have a high concentration of potassium inside the cell, low concentration of potassium outside the cell. So that's the chemical driving force. In order for us to not see potassium movement, the electrical driving force would have to be the exact same value, so the exact same magnitude in the opposite direction, okay? And so what would happen is those two forces would just net each other out. Remember, thinking about minusing the smaller force from the larger force, if they are the exact same value, let's say we have a chemical driving force of -50, let's say we have a chemical driving force that's the value -50 wants to move a particle into the cell, and then an electrical driving force, same thing, -50 that wants to move a particle outside of the cell. Those two are the exact same value. So if you subtract that, 50 minus 50 is 0. And so now we have no force. They've both netted each other out, okay? And so the particle is not going to move. All right, I hope that was clear. I hope that made sense there in terms of that question. So when the electrical force is equal to in terms of the magnitude, but opposite in terms of the direction of the chemical force, then we have no movement of said particle. Both of those forces have equal and opposite directions and magnitude, and so it just nets each other out. Okay. I'll go back here so you can kind of write this response down and just kind of review it when you're studying this. All right. Now, the next thing we'll speak about here is called the equilibrium potential, and that's what we just described. This is the membrane potential at which the electrical force is equal and opposite to the chemical force. In other words, the particle does not move. Okay, and it is different for every single ion. For potassium, it happens to be -94. And so what that means, right, having an equilibrium potential of -94, that basically means when the cell is at this membrane potential at this value at -94, potassium doesn't move. Potassium's electrical force is equal and opposite to its chemical force, and so it simply goes nowhere. It doesn't move. It's at equilibrium. Okay. All right, I'm going to pause here and see what questions we have before we keep going. And I think we'll reserve the rest for Monday. I don't want to keep kind of going here. I want us to kind of take this in strides and add layers as we go. So far we've spoken about the chemical driving force separately, electrical driving force separately, and now we're beginning to combine those two forces and talk about how we figure out where does this particle actually go. If it's got two different forces trying to move it in two different directions, where is it actually going to go? And so we said back here that we're going to take the stronger force, we'll subtract the smaller force, and we're going to get a value for the force. In terms of finding out the direction of where it actually goes, it's going to favor the direction of the stronger force. Okay. All right. And then we lastly here got into this idea of equilibrium potential, which is the membrane potential at which a particle is no longer moving because its chemical force is equal and opposite to its electrical driving force. And again, the value of the membrane potential is different for every ion. Specifically for potassium, potassium's equilibrium potential is -94. And just to reiterate what that means, when the cell is -94 millivolts inside with respect to the outside, that is the membrane potential at which potassium has an electrical force that nets out its chemical force. And so potassium is at equilibrium and it does not move.